So let's look at this neat graph. We have heat of fusion and heat of solidification down here. The same, but different signs. That's low heat, low enthalpy. So going from a solid to liquid equal as going from a liquid to solid. It takes the same exact number of heat, amount of heat I should say, but just different signs. And the same token, going from heat of vaporization and heat of condensation are exactly the same, but different signs. So melting will take the same as solidifying. So the heat lost will be the same as the heat lost when we solidify a piece of material is the same as the heat gained when we melt. The heat lost when we condense a substance is the same as the heat gained when we vaporize. Let's look at this example. How much heat kilojoules is absorbed when 1 liter of water is boiled as is converted to steam? Well, if something is converted to steam, that means we're looking at the heat of vaporization. Okay? We're making vapor out of it. We need to find which water again, so let's look at the value of that. All right, so here is heat of vaporization of water is 40.7 kilojoules per mole. So that's what our value is. Heat of vaporization, 40.7 kilojoules per mole. We want to know how much heat is absorbed. So we have our formula, delta H equals mole times delta heat of vaporization. But the problemo, we have moles and then we have liters. We don't have grams. But if we remember our conversion, 1 milliliter of water equals 1 gram of water. So that means 1 liter equals 1,000 milliliters, which equals 1,000 grams. So from 1,000 grams of water, we can get mole. Very exciting. So we have 1,000 grams of H2O, 18 grams of agua, we have 1 mole. Let's calculate that. So that is 60 mole with sig figs. So in about a quart of water, we have 60 moles of water. It's kind of interesting. Now from that, we can get our delta H equals mole, which is 60 times 40.7. And then with our sig figs, we have 2,000 kilojoules. That's how much heat is absorbed. We only have that one sig fig to start with. Now let's look at this problem. How much kilojoules of heat are released when 1 liter of Everclear, a rectified spirit, which is about 95% pure alcohol, freeze? Assume it is 100% pure alcohol and is put in a freezer, able to go to a negative 114 degrees Celsius. Now, Everclear is probably one of the most potent alcoholic beverages out there because it's 95% pure alcohol. Most of the alcoholic drinks that are purchased are much less than that. Beer is about 3 to 10% alcohol. Wine's about 15% alcohol. Some of your harder liquids, like whiskey, scotch, those maybe 50, 60%. So 95% is almost pure alcohol. And you'll notice that maybe your parents might keep some alcohol in the freezer, and alcohol will not freeze at freezer temperatures. Water will freeze at 0 degrees Celsius, but most freezer temperatures are about negative 25 degrees Celsius or so. And alcohol will not freeze unless it's much, much colder. That's a lot colder than negative 10 degrees Celsius or 25 degrees Celsius, negative 114 degrees Celsius. So if we are actually to freeze a liter of this potent Everclear, how much heat must be taken away from it? How much heat must that freezer work at removing from your Everclear? So let's look at an example here. Let's find our formula. Delta H, that's what we're looking for, equals mole times delta H. So we are removing heat, we're freezing it, so it's heat of solidification And again, a heat of solidification is the opposite of the heat of fusion. So what is the heat of solidification or fusion for pure alcohol? So let's look that up. All right, so we see here that we have all of the...
Who are you talking to?
Okay. Here's our heats of physical change, and we have all these to choose from. Now, alcohol that we notice is there's two different alcohols here. There's a methanol and the ethanol. The alcohol that we drink is ethanol, so that's the heat of fusion we want. So we're going to use 4.60. So we have delta H of fusion for alcohol equals 4.60 kilojoules per mole, but we're using the delta H of solidification, and that's just going to be equal negative 4. So we want delta H equals mole times delta H fusion. Again, 1 liter of Everclear, 1 liter we found out to equal 1,000 grams. And so 1,000 grams from the same problem as last time equals how many moles? So that again equals 60 moles. And let's just plug this in. So we have 60 moles, delta H equals 60 moles times negative 4.60, which with significant figure is negative 300 kilojoules. So that means we had to take out negative 300 kilojoules from that liter of alcohol in order to freeze it to a solid chunk.
Okay.
So what is the molar heat of solution? Molar heat of solution is the enthalpy change, or the heat change caused by a dissolution of 1 mole of substance. So when a mole of substance goes into solution, we have a heat change. So again, during the formation of a solution, heat will be either released or absorbed. So as a reminder, a solution is something like Kool-Aid. You take a little packet out, and you have a little Kool-Aid drink. You put it into some water, and you mix that powder into the solvent, and we have a solution. And in that case, heat will be either released or absorbed when we're making our Kool-Aid solution. Tasty. Here are some enthalpy changes of solution for some selected compounds. So they range from a negative 74.84 for hydrochloric acid, all the way up to a 25 for ammonium nitrate. And we're also using kilojoules per mole. Let's try a fun problem. How much heat is absorbed when a teaspoon of salt dissolves in water? So the delta H solution, salt is 3.87 times kilojoule per mole. So when we say salt, there are many different types of salt, but we'll assume it's sodium chloride. So we have delta H, that's what we want to know. Delta H of solution is 3.87 kilojoules per mole. Now we want to know the moles of salt, sodium chloride, in 1 teaspoon, which is about 5.7 grams. So if we have 5.7 grams of sodium chloride, we'll first figure out the moles here. 1 mole of sodium chloride, we get 0.098 moles of sodium chloride. So let's just plug this in. 0.098 times 3.87 equals, that's 0.38 kilojoules. That really is very little. So when you're dissolving just a teaspoon of salt in water, you're really not getting much heat release. It's some, but it is interesting